Go. So section 7.7 is going to discuss numerical integration. It's basically kind of a brute force way to calculate the area between a function and the x-axis. So let me remind you a little bit about what we've done till now. So right now we've got kind of a very, very small Riemann sum. And if you take a look, we're measuring the height of the rectangles here, and I've only got two of them. Measuring the height at the left-hand endpoint. Measure that height there, multiply by the width, and then that's the area of this rectangle. And then you repeat that process for this point here. Now, obviously we don't got a really good estimate of this area because our mesh is so coarse, or our partition is what we call this, the way we divide up the interval over which we're trying to find this area. Now here's our function right here in case you're curious what that is or tried to mimic it. Now do you remember our assignment from section 5.1? How can we improve the accuracy of this method? What was the big conclusion that we got from there?
Smaller intervals.
Smaller intervals, yeah. More rectangles. So if we look here, we've got two rectangles and we get an estimate of the area of about 8.4. It's not really good. In fact, we got a 21% error in our estimate if you actually compared it to the real value. So you start adding more rectangles and get better and better estimates. Now we've got the error down to less than 5%. That's not too bad. But even if you dial it all the way up, adding more and more rectangles, you're still not going to get down to less than 1% with 25 rectangles. Now there's other methods that we looked at as well. You might remember that instead of using the left-hand endpoint, we also looked at using the right-hand endpoint. So let's take a look at the right-hand endpoint. If we do that, then that changes things up. Our height comes from the right-hand endpoint of our interval. And again, it's not really a great method just to use the right or left-hand endpoint. If you add enough rectangles, like we can do here, then you are going to improve your estimate of this area. But there's more clever things we can do. One very simple thing that we can do is use the midpoint. So here with 25 rectangles, we're still not down to less than a 1% error. So let's use the midpoint. And the midpoint, well, that's better. And with the midpoint, and let's see, we've got two rectangles. Let's dial that up. 3. So with like 4 rectangles, now you're down to within less than a % error. So that's pretty good. But even this is kind of a crude method, and we're going to start to try and improve on that. So how are we going to improve on that? We're going to use other methods. So one of those methods, and let me dial this back down to 2 here, is instead of using a rectangle, how about if we used a trapezoid? So let's take a look at what it is if we use a trapezoid. So let me move this over here. So in a trapezoid, we're trying to follow along the curve a little bit more. We're not just using a flat rectangle, we're using something with a little bit more shape to it. And that doesn't look too bad. With just two intervals, we're already less than a 1% error. And if you dial that up in terms of the number of intervals, you know, more and more trapezoids, you get a pretty good estimate pretty fast. Look, with a modest 10 intervals, our error is down to about less than 1/4%. That's pretty good. But wait, there's even a better idea around. So this is called the Trapezoid Method. And, you know, it's not bad. But a much better method is something called Simpson's method. So let me just write those things down. We've got trapezoid method and Simpson's method. Simpson's method works a little bit different. Now, let me take a little step away from this for a second and look at 3 points. Now, everyone knows that 2 points determine a line, but are you guys aware that 3 points determine a parabola? In fact, if you wanted to play with this, I could share this link with you real quick through the chat. No matter what you draw, 3 points will determine a parabola. So I can move this point anywhere I want, and wow, there's still always a parabola that fits through it. Or if I move this point, and so on. No matter what, I can move these things around, and there's always going to be a parabola that fits through those 3 points. So, okay, well, what does that have to do with our attempt at finding areas underneath the curve numerically? Glad you asked. Well, what we can do is, instead of trying to fit a trapezoid here, what if we try and fit a parabola? In fact, let me go all the way down to 1 interval. So there's 1 interval with our trapezoid. Probably doesn't look like a good fit. Let's take a look at this last method. And when we fit a parabola as opposed to just a trapezoid, we're going to get a much better approximation of this area. So let's switch over to Simpson's method, which is the last method we're going to look at here. Let's see. Come on. Simpsons. Oh, sorry. Wrong one. This one up here. There we go. That's Simpson's method. So what you can see now is that we've got a parabola that's being used to estimate this area in this 1 interval. So a much better fit. And even with just 1 parabola, 1 interval, well, 8%. That's not so great. Let's dial it up. We'll see what happens to the error. Well, with 2 parabolas, wow. Now you're less than 0.2% error in your estimate with just 2 intervals. That's pretty outstanding. If we dial it up to like 10 intervals, that's pretty amazing. So that's our error, less than 0.3/10,000%. That's really good. So this is just an example of a numerical method. It's a way to try and find the area between the curve and the x-axis over some interval. But how do you apply that, if you're stuck doing this by hand? Well, we'll do a couple examples of doing this by hand. And the handout that I gave you kind of shows you how this works. So if you want to estimate things, then you can use this method, which is called the Trapezoid Rule. What you're going to do is you're going to divide up your interval into certain subintervals. That's going to be your partition. And they're all going to be the uniform width. Now that width is something that we call delta x here. So that's this part right here. So that's going to be the same. And you're going to multiply by delta x divided by 2 times this expression. Now, the thing about this expression is that there's a nice little pattern here. You should notice the pattern of the coefficients. The n terms, in terms of values of f, have a coefficient of 1. Everything else gets a coefficient of 2. This makes it more efficient in terms of implementing on a computer or a calculator, etc. But your delta x is just going to be the width of your subintervals. And then the x sub I is just going to be the points along the way. So we're going to look at one example here. And it's this one. We're going to apply the trapezoid rule and Simpson's rule to approximate this interval. There is this integral. Now, why would you want to do something like this? Well, this comes up quite often. A lot of times you cannot find an antiderivative for a function. And if you can't find an antiderivative, well, a lot of times we still need to evaluate these kinds of expressions. So let's take a look here. The integral from 3 to 6 of sine of x sine of the square root of x. Where'd my Photoshop go? Oh, here it is. There we go. So 3 to 6. Sine of the square root of x dx. Please put that dx in your work. There's good reason for it. I'll share that with you later. All right, we want n equals 6. So we want 6 subintervals. That's going to mean we're going to need a total of 7 points to line up those 6 subintervals. Now, I'm not going to try and draw this function. I don't know what it would look like. I mean, certainly we can go to Desmos and graph it there. What I want to pay attention to, though, is all my little subintervals. So 3, 4, 5, 6. So that's coming from here. And then 3.5, 4.5, 5.5. If you notice, I've got 1, 2, 3, 4, 5, 6 subintervals. So this is my partition. Now, according to the trapezoid rule, what we've got to do is take delta x divided by 2 and multiply it by the function, which is coming from this part right here, multiply by the function, and in some cases we need to multiply it by 2. Okay, so what all is that going to look like? Well, let's find delta x first of all. Delta x is going to be b minus a over n. So let's do that. Delta x equals b minus a over n, which is 6 minus 3 over 6, or 1/2. Okay, the width of our intervals is 1/2. Certainly we can see that. What else do we need to know? Well, we've got all our points here. So we're going to be evaluating the function at these points and then multiplying it by 1/2 divided by 2 times that funky expression we get from the trapezoid rule. So what's that all look like? There's your delta x over 2 times f of 3 plus 2 times f of 3.5 plus 2 times f of 4 plus 2 times f of 4.5 plus 2 times f of 5 plus 2 times f of 5.5. And one last one. Does anyone know what that last one would be?
Two f of 6.
Close. The first and the last ones get multiplied by a 1. So it's just the way the trapezoid rule works. There's a 1 here and a 1 here. So yeah, the endpoints are a little different. And now comes the fun part. We've got to evaluate the function at all these different points. So trying to think if there's a clever way we can do this on, say, Desmos or something like that. Because I'm not really a big fan of trying to do this all by hand. You can. Now the function that you have to deal with, f of x, comes from your integrand. So that's your f of x. So you have to do the sine of the square root of 3, or the sine of the square root of 3.5. And that's just looking mighty unfun. So sine of the square root of x. So it's kind of up to you. I can show you how to do this on the graphing calculator or Desmos. I don't think it's going to be something that really comes up to you very much, because the methods that, say for instance, your calculator uses are much more sophisticated than the trapezoid rule or Simpson's rule. These are some real entry-level things. You get into some fun stuff where you don't make all these points evenly spaced. So Romberg integration would be a possibility. A lot of different fun and cool things, but way beyond this course. This is just a little survey of, you know, a couple of the basic methods that you use to try and find these try and find numerical estimates of this thing. All right, so that's going to be 1/2 divided by 2 is going to be 1/4. F of 3, that's going to be the sine of the square root of 3 plus 2 times the sine of the square root of 3.5, and so on, all the way down to 2 times the sine of square root of 5.5 plus, and the last one is going to be the sine of the square root of 6. Like that. All right. Well, most likely you're not going to get a chance to do this in class with Desmos. So let me show you what you could do on a graphing calculator that might be a little bit more efficient than just doing this by hand. You know, let's see. Is there a way I can finesse this? I don't know. Let me just give you kind of a brute force approach. Then I'll also give you some finesse if you're terribly interested. So I think I would start by programming in the function sine of the square root of x make sure that you're in radians. Calculus is done in radians. If you were in degrees, it would mess everything up. Let's just double check that our table settings are correct. Second table set. You want independent set to ask. That way you can type in whatever values that you want. So I'll delete these values here, and you can kind of keep up with my keystrokes by looking at the bottom here. So I'll delete, 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 delete. There we go. And now just type in the values that we need. So that'd be the values that are part of our partition: 3, 3.5, 4, 4.5, and so on, all the way up to 6. Okay, now we can just replace our values in our expression by these numbers. Now, if you want more accuracy than what you see here, which is only 4 digits, if you cursor over and highlight these things, at the bottom of your screen, you'll see as much accuracy as you want. So for instance, this looks like 0.987. It's gonna be 0.9870 something, etc. So you get as much accuracy as you want. Filling things in here. Let's start out with 1/4 of the sine of square root of 3. So coming back over here, sine of 0.987 plus 2 times 0.9553, and so on, plus 2 times 0.9093, and 2 times 0.8523. 2 times 0.7867. 2 times 0.7148. And finally, with the last one, you don't multiply that last one by 2. It's just the way the formula works out when you start doing this for multiple intervals. So 0.06382 or 0.6382. There we go. And then add them all up. Let's see if I can't speed up that process a little bit. Visually, this is what we're looking at. So this is our interval, 3 to 6. We've got different subintervals. Actually, we got too many there. Let me change that. We don't want 10, we want 6. 6 subintervals. And with the trapezoid method, that would be this one over here. If we did all the arithmetic on that, then we would end up with 2.5152. Uh, 2.51552, etc. would be the answer that we get out of all that. So, yay. Feels like an awful lot of work for us to do by hand. And that's why I'm not a big fan of making you go through this. But it is something that I'd like you to understand. Some points, you're going to need to find an antiderivative or the area between curve and the x-axis for some function for which there is no antiderivative. A very famous one for which there's no antiderivative, very simple one, is the integral of e to the x squared. And this one comes up in statistics, or e to the negative x squared. Comes up in statistics. There's no antiderivative there. And yet we need to work with that formula all the time. There's a lot of statistics that are based on that. Okay. How are we looking on that first one? Doing all right there? Let's take a look at Simpson's rule. So Simpson's rule, we're going to be using the same kind of points. It's just a little bit different coefficients and a little bit different number out front there. But it's going to be more or less the same idea. So let's go back to our little handout. Take a look at the difference between this and Simpson's rule. Now for Simpson's rule, you've got a different term out in front. Basically, it's our delta x divided by 3. But take a look at what's in the parentheses. Notice you've got a different pattern here. So the pattern here in parentheses isn't quite the same as it was for the trapezoid rule. One thing that is the same is that our first 2 terms, or our first and last term, like this one here and this one here, have a coefficient of 1. But the rest of the way, you have this interesting pattern of 4 and then 2, 4 and then 2, 4 and then 2, etc. So much different than the trapezoid rule. But you get much better results with Simpson's rule. Much better. Better than actually you should be able to expect. So, but that's getting into numerical analysis. Let's take a look at it with Simpson's rule. Simpson's rule. All right. So we're going to, again, use the same function and same partition. So with n equals 6, f of x is the sine of the square root of x as before. Our interval is going to be 3 to 6. So that means our delta x is going to be 6 minus 3 over 6 again, which is going to be 1/2, just like it was just a minute ago. But out in front, we got to put delta x over 3. All right, so a little bit of a difference there. So it's going to be 1/2 divided by 3. And then f of 3. And now you got to start with your repeating pattern. That should be a 3.5 there. Well, what coefficient is going to go in front of the f?
4.
Yeah, 4. It's going to be a 4 here. And then the next one, the next coefficient, is going to be a 2.
2.
Thank you. F of 4. And then 4, f of 4.5, and so on. Plus 2, f of 5, and 4, f of 5.5. And what's the last one? What's the last one that you would do there?
Is it just
f of 6?
Yeah, well done. Just f of 6. Yay. And I'm not even going to bother to put a 1 there. Okay. 1/2 divided by 3. That's just 1/6. So it's going to be 1/6 of all this stuff. F of 3, or sine of the square root of 3 plus 4 times the sine of the square root of 3.5. 2 times the sine of the square root of 4, which I know is 2, but I'm not going to bother simplifying it, plus 4 sine of square root of 4.5 plus 2 times the sine of the square root of 5 plus 4 times the sine of the square root of 5.5. And lastly, plus the sine of the square root of 6. Yay. Now, I'm not a real big fan of plugging this into my calculator. So if it's okay with you, how about if we do this last one with Desmos? Want to do it with Desmos instead?
Yeah.
All right. So let me just get a new one here. I'm going to define a function to start with. I'll call it f of x is the sine of the square root of x. So here we go. F of x equals the sine of the square root. And if you ever want to, you can just type in like SQURT, and then bam, there you go. There's your square root. The alternative is to hit the keypad here and then use the square root of x. X inside, thank you. Now the cool thing is that Desmos works just like your graphing calculator. So if I want the sine of the square root of 3, you know what? I could actually type that in, or I could just do f of 3. Yay. And I could add 4 times f of 3.4, or excuse me, 3.5, and so on, plus 2 times f of 4, plus 4 times f of 4.5, and so on. And I think I'm liking this a little bit more than I like doing it on the graphing calculator. F of 5, and just 2 more, 2 times, that'd be 4 times f of 5.5, and then f of 6. Yay. Now that's almost what we need. If you remember, I need to multiply that value by 1/6. So it's going to be 1/6 of, let's see, we ended up with 15.1069. So if I divide that by 6, take this, copy it, divide it by 6, there we go, 2.517. Chances are it's much more accurate than our estimate from the trapezoid rule. But at least what can make us feel somewhat comfortable is that this answer here is reasonably close to this answer here. They're different by less than 2 10,000ths, or maybe a little bit above 2 10,000ths. So pretty close to the same thing. Which way do you find more efficient in terms of graphing calculator or Desmos? Which way would you do it if you were doing it at home? Just like, okay, I got to get this done. Just wouldn't do it at all?
I kind of like the calculator because that's what I'm used to.
Okay, all right, good to know.
I thought Desmos was easier.
All right, so 1 for Desmos, 1 for the graphing calculator, and 20 abstentions. Fair enough. All right, that's about it. We can do another example if you'd like, but I'm not really going to be asking a whole lot about this.
You went really strong with these 2 examples.
yeah, make these examples go a long way. I mean, the bottom line is that, you know, like I said, your graphing calculator, Desmos, any place that does numerical integration is going to do something much more sophisticated than this. What you want to keep an eye on is the fact that, you know, if you've got a nice, well-behaved curve, something like this, that, yeah, you're going to get a pretty good estimate with numerical integration. In fact, a really good estimate. So, I mean, with Simpson's rule here and n equal 25, our error is about a 0.010%. That's probably going to be really good for most applications. But Simpson's rule is a lot less accurate than other stuff that's out there. And that's what, you know, you're probably going to end up using when you use your graphing calculator or Desmos to do these things. So, any other comments or thoughts on this?